Welcome everyone to lucky episode 13 of our Block 74 Apollo Guidance Computer Replica project. Today we're going to be covering or kind of wrapping up the X register and summer, or the adder that we've talked about in the past two videos. The first one, we talked about the X register and kind of how it operates, and it's a little bit unique in how data is written into the X register. There's several constants that can be written into the X register, um, and some data that can come in from the A register. So a little bit unique in that it doesn't read, or you can't write directly into the X register from the write lines. In the second episode, we talked about the adder, which forms kind of the arithmetic unit of the Apollo guidance computer, and how it adds the contents of the X and the Y register. And today we'll talk about the output, how data gets out of, now is what we call kind of the U register, or the summer, the outputs of the summer, or arithmetic unit. So when we start looking at the control pulses around the U register, or the summer, we'll notice some similar behavior as to what we had to deal with on the A register. So you can see here we've got both a RC and an RU simultaneously. So if we just dealt with this normally as we would with our octal transceivers, we'd potentially encounter bus contention. This is similar to what we had to deal with when we designed the A register, in that we can't, read the contents of two registers onto the write lines simultaneously. And the Apollo guidance computer deals with this in that the write amplifiers that it used, so that how it would actually basically cycle data back onto the write bus, or the write lines, is that it would perform a logical OR function between all the contents that are being written. So in this case, it actually would OR the contents of anything within the C register, anything within the U register, and then those outputs would be written into in this case, the A register. So this is as part of this R, A, and D sub-instruction. And if we look at, there are a few other cases. There's the W, A, and D instruction, the R or ROR instruction, and the WR instruction. In this case, there's also, in these we do the RC and RU into the accumulator, the A register. Here it's RB and RU, and then here we have RB, RU, which is then read by both the accumulator and the IO channels. So it's okay. We can have two simultaneous write commands, because that means we're just going to take whatever's on the write line bus and read it into either the contents of in this case, an IO register, or the accumulator. So that's fine. One thing that we learned, and we had a little bit of a cycle back in one of the previous episodes where we talked about, like, do we have to do, like, is this a and onto the bus, or an or onto the bus? We looked at the XOR, the exclusive OR function, when we were dealing with the A register. And actually, as we kind of dug into it and had some of the comments that came in from followers of the channel, is the sub instructions and kind of the actions that take place actually use some Boolean logic to actually do the appropriate logical function. So based on the sequencing of how data is written to the various registers as we go through the process, we'll either perform a logical and, a logical or, a logical exclusive or, and all we have to deal with, at least on the write lines, is just do a logical OR. So it kind of simplifies things, in that we don't have to have the ALUs that we use to kind of perform these logical operations, like we did on the A register, perform different instructions. They can all just be kind of hard coded to either pass everything through if we're not running one of these kind of composite instructions. And if we are, then we can perform the logical OR. So this is very, very similar, again, to what we had to do with the A register. So we have to use these kind of technique of the clocking, where we kind of have these kind of subsections, where basically what we'll do is we'll read the contents of the B or C register onto the bus. So we've got kind of a special timing pulse for that. Then we'll perform our logical operation. So in this case, the logical OR. We'll then latch and hold the data so that we can then read that data out onto the U bus. And then from there, we can then write it into the A register or the channel register from the bus. That means we have to use kind of the same pull forward of read timing for the BC register. So this is kind of the logic that we identified when we were designing the A register. And I've implemented that onto the B/C register in order to kind of, in these circumstances, it'll kind of do this special read timing in order to kind of put that content a little bit early onto the write bus so that we can do the logical operation. And then we want to delay the read timing, in this case, onto the U register based on the sub instruction, which is a kind of combination of a variety of control pulses. So that's, I'll just quickly kind of look at the logic of how we kind of, the circuitry and how we put that together. So a few things, and this is what we've been looking at over the past couple episodes with the A register. So here we have the kind of that special clock generation, that circuitry that we basically copied from the RA or the A register layout. I'm kind of thinking back and forth whether I should just implement this once on the clock card so that we don't have to implement it in a few places. I'm just doing some determination if I have the appropriate real estate on the clock card or not to basically accommodate a few of these other chips. So we'll see if we can do that in one place rather than having to replicate it. And then here we have some of the logic which determines that kind of delay reading of data so that we can do the latching and logical function. Here are the same ALU chips that we used in the A register to perform that logical OR. It's probably overkill in this case because we're just doing an OR function, so we're not using a lot of the capabilities of these ALUs. These ALUs can do addition and subtraction and a wide variety of Boolean logic. But when you actually look at the fact that we'd have to do OR gates across all 16 write lines, so and the 7-4 series chips that has the OR gates on them, there's only 4 gates per chip. So we'd be using 4 chips containing the OR gates to perform that logical function. Plus, we'd have to have some control logic because we only want to perform that ORing of the write lines when we have this kind of sequence of sub instructions. So we'd be looking at a lot more than 4 chips to basically build out this functionality. So just to save a little bit of real estate on the boards, we're going to use these ALUs. And since I was able to order or basically secure a surplus of about 15 or 20 of these, I've got extras lying around, so why not? So if you want to look at the episode where we talked about the A register, we'll kind of talk a little bit about the functionality. Again, one thing that's different is we only need to perform the logical OR. So that's basically these S0, S1, S2, S3 is basically what command, what we're telling you can see through this decoder, what we want to tell the ALU, what logical or mathematical instruction we want it to perform. In this case, we only need to worry about doing the OR function, which in this case is, we can basically set all of S1, S2, S3. We can just ground them so set them to 0. And then we've got our S0, which we either set high or low, depending if we just want to do a pass through or we want to do the logical OR. And then all of that data heads out onto our latch, where we use the appropriate kind of read timing based on that circuitry we just talked about. And then there's some logic to enable based on when we're being asked to read data out onto the write lines. Now, in the case of the the X register, or the U register in this case, because it's the output of the summer, there's kind of two additional scenarios that we have to deal with. So there's a RU control signal, which reads the data out onto the write bus. There's also this RUS instruction. And the RUS instruction, what it'll basically do is it'll take and basically determine whether it's asserted or not, whether we write the contents of basically, write lines 1 through 16 out onto our bus, or if we basically take the contents of 16 and place it into 15. So if we have an RUS, we basically take whatever is in our basically the 16 content of our summer, and we also write it out onto the 15 write line. So we've got a little bit of logic here that deals with that particular scenario. You can kind of look at kind of simulate that logic. If I can just find where I hit that, there we go, here. We've got kind of this logic here. So normally, we're just going to pass through whatever is in the adder or the sum contents 15 or 16. We'll just pass those straight out to the write lines. But if we assert, and again, we have our low control logic, if this is asserted, then you'll see whatever is in A6 or in our 16 doesn't matter. We write the contents of 15 to 16. I think that's what I said earlier, but if I didn't, it's yes, we want to take the contents of our 15-bit in our summer and write that out to both the 15 and the 16-bit contents of bit 15 and bit 16 of our write line. So that's this logic that we put here, and that's kind of how we determine how we write out the contents there. One other kind of unique aspect of the summer or the U register is we have this U2 BBK control pulse. And this is basically, we want to load some of the contents of our U register out to some of our memory bank registers. So we'll talk more about this when we talk about our S register, which is our memory address, because the AGC, the S register, which is kind of the address register, is only 12 bits wide. We'll talk about why that's the case in the episode on the S register. But if you realize that 12 bits doesn't give us enough address space to address the entire contents of the AGC's both RAM and ROM memory. So the AGC uses banking, and basically there's a couple of bank registers that we use to be able to address the full memory space on the Apollo guidance computer. So there's, based on some of the instructions, there's a command or a control pulse, this U2BBK that we just talked about, that will load or basically take some of the contents of the U register and either write them to our eBank register or our FBank register. So again, we'll talk more about that and what these banks are when we talk about the S register, but we just have to implement this in our X register and U register just so that we can actually bring those contents out appropriately. So we created a little bit of logic here. This is basically similar to our normal write logic. We don't have to worry about that, the bus contention and managing that for this case. So we have, if our U2 BBK control pulse is asserted, and we have our write timer, we will go low, which is our chip enable low we'll just use a normal 8-bit or octal transceiver to push those 8 bits out into the appropriate FBank and eBank registers. If we go back and just look at the kind of bill of materials on the X register, you can see it's quite a lot. I will be posting. I still have an old picture of the Q register here because I'm actually in the process of building the X register right now. But you can see there's quite a bit of glue logic and logic and just like storage on the card itself in order to perform all that functionality. So we've got our D-type registers, which is the contents, the actual X register contents. We've got uh, our line selectors, so that we can either bring in our constants or the data from the other registers. We've got our adder, the chips we use to add. We've got the latch that we're using in order to kind of store the data, so we can write and hold that on the write line, so that we can then write it into our either A register or channel register. We've got our bus transceiver. This actually should be one. There's only one of them, not two. And then we've got our function or ALU function generator to perform some of that write logic or write line logic that we need. And then a whole bunch of glue logic for everything to work together. That means that we've got about 34 chips in total on this one. So it's definitely the most complex that we've built so far. And this is why on the second set of boards that I got built or made for this project, I took this card and I extended it to add another 2 rows of real estate. So I can now have up to 35 chips on a single card. So we're getting pretty close to capacity, but that should be able to handle everything going forward. So again, thanks for joining. I won't be posting an episode next weekend. I'll be out of town on vacation, but I will be back in 2 weeks, and haven't decided yet if we'll dive right into the S register or if we'll spend an episode looking at some of the hardware, because I do have enough cards built as well as the backplane built where we can start actually, issuing control pulses and getting some functionality to occur, so we can transfer data from one register to the next register. We don't, of course, haven't built our the actual control pulse logic yet, so we're not going to be able to automatically run instructions on the AGC, but we can at least manually load data into registers and read data out from registers onto the write bus and start to actually test these boards out and make sure that they're working the way that we expect. Anyways, thanks everyone for joining. As always, please subscribe so you get notified when our next episode comes out. And I'm always looking for feedback. Like I said, this is a bit of a exploration for me. I'm learning a lot and learning all the different interesting design decisions that the folks that created the Apollo guidance computer made throughout the process, and interesting to see how they took advantage of some of the quirks, if you will, in order to create the programming used to run the actual mission software. Anyway, again, thanks, and we'll see you in 2 weeks.